Uh, so, hi everyone. I'm filling in for Bunyamin, who had another obligation, although you might see him here for some reason. So other than that, it's my pleasure to introduce Johann Langemets. I hope I said that correctly.
Yeah.
From the University of Tartu, and he's going to talk to us about a characterization of Banach spaces containing L1 of kappa via ball covering properties.
Yeah, thank you for that nice introduction, and thank you very much to Bunyamin for giving the opportunity to give a talk in this webinar. And I think this has been one of the few good things about this Corona crisis we have had all this year round. So it's great to see all those nice webinars here. So today I will speak of the title, as Pavlos already mentioned. This is a joint work with one of my PhD students, Stefano Cerci, and our co-supervisor, Alexei Lisitsyn. So this talk is mainly based on our recent preprint, which we uploaded, like, I think, at the very end of February, probably. And so today I will talk a little about the background, what is the motivation, and what was the problem we tried to solve. Then I will introduce some notations which might seem a little bit technical, but they're just for convenience. Then the main result about these renorming Banach spaces. Then we will briefly look into stability in direct sums, just to see how it behaves in comparison to other known results. Then we will define something which comes quite natural when you study these things, some new kappa octahedral norms, present some examples and classes of spaces where these new definitions or these properties are equivalent, and some and in general they are different. And finally I will finish with posing a couple of open problems which are interesting to me, and I hope they will be interesting to some of you too. So first of all, a little bit about the background. So this is a little bit repetitive after Professor Avila's talk last Friday, but I can't escape it. So in 1989, Godefroy and Moret defined a Banach spaces being octahedral or having an octahedral norm if for every finite dimensional subspace and for every epsilon there is another element y, such that the triangle inequality is almost like equality modulo epsilon. So it has very much like the behavior of L1 norms. And classical examples of classical Banach spaces are L1. In particular, every L-embedded space is octahedral. And these three other spaces represent the class of spaces with the Dagovet property. So all of these spaces are octahedral. And moreover, if you have heard of Dagovet property, then it is also true that their duals are also octahedral. So not only the space, but its dual also. But anyway, later on, I will briefly remind what this property is. Now, if we look at separable Banach spaces, then Godefroy and Galton showed that this having an octahedral norm is equivalent to an existence of an element in the bidual, which is L-orthogonal to the whole space. So you have something in the bidual which is L-orthogonal to everything. And this is what mainly was the main topic of Professor Avila's talk last Friday, when they studied conditions when these elements exist. And by now we know that separability is essential. Gines Lopez and Abraham Rueda proved that if you remove separability, then this is strictly a stronger property. And the existence of these L-orthogonal elements was very thoroughly and nicely discussed in the last webinar. Okay, so some small observations. So if the bidual is octahedral, then it passes down to the space itself. And this is very easy to see via this principle of local reflexivity, because you have something in the bidual, which is L-orthogonal to every finite dimensional subspace in X, and then you can push it down modulo some epsilons, and then you get that this space is octahedral also. However, the converse is false in general. So, for example, the space of continuous functions is octahedral, but its bidual fails to be octahedral. However, up to renorming, everything is okay. So Godfroy proved that the following assertions are equivalent. So if a Banach space contains a subspace isomorphic to L1, if and only if it can be equivalently renormed to be octahedral. So, however, I will make a just brief detour. So, on the other hand, he also, bearing in mind this example that in general the bidual is not octahedral, then he proposed the problem whether every Banach space which contains L1 can be renormed in a way that its bidual is octahedral. So a strengthening of this term, that if you can renorm the bidual, then of course you get the original space also. And this stayed open, and actually in full generality is still open. And however, a couple of years ago, together with Gines, we were able to show that this is true for separable Banach spaces. However, as you can think, the first non-separable Banach space you can think of, so little L infinity, we don't know the answer. So as soon as we remove separability, I think almost anything is unknown. At least I haven't seen any papers about solving this question. So as a sub-problem, even this little L infinity case is open. So this is for motivation. And now, however, in that paper from '89, Godfroy also had a very nice remark that we can characterize octahedrality also with another condition. So a Banach space is octahedral if and only if you can cover the sphere with, well, if you cover the sphere with a finite union of balls centered at xi and with radius ri, then already one of these balls must contain the whole unit sphere. So, and this makes a connection with these octahedral norms with coverings of the unit ball or coverings of the unit sphere. And some time ago, there was a nice survey paper by Pierluigi Papini, because there are many different indices and properties revolving around covering the spheres or balls in the unit ball of Banach spaces. So, and what we were interested in was the following property. Well, later I will explain why in particular this thing. But in 2006, Lexington defined a Banach space or a norm space having the ball covering property if its unit sphere can be covered by countably many closed balls that do not contain the origin. So by definition, it is quite clear that every separable Banach space has this property, because you can take the dense sequence in the unit sphere, and you can choose whatever radius you want, basically how small, and you have a ball covering. But this little L infinity is always probably the first non-trivial example of a space having this property. In that paper, he also proved that if X has this ball covering property, then its dual is weak star separable. Now the converse fails in general. However, in 2009, Font, Zanko, and Cheng, Shi, and Zhang independently proved that the converse is true up to renorming. So if the dual is weak star separable, then for every epsilon, there is an 1 plus epsilon equivalent norm on X, such that X has this ball covering property. So we have an if and only if in terms of these ball covering properties. And there have been some various papers by many authors about this property, how it is stable with different sums and so on. But I don't have the time to explain them all. However, in 2009, Cheng and Shi extended this ball covering property to alpha ball covering property for positive alphas. So they were first to extend it to positive alphas, and they say that this space has this alpha PCB for positive alphas if its unit sphere can be covered by countably many balls that do not intersect the alpha times the unit ball. And 10 years later, Girao, Lisitsyn, and Montesinos also considered this alpha PCB for negative alphas because it behaved rather differently from the positive ones. And this we will see also today. However, in this condition, that we require that the balls don't contain alpha times the unit ball. So in the picture, this original, in other ways, zero PCB corresponds to the case that you can cover the sphere with countably many balls with centers A and with some radius that do not intersect the origin. So imagine that this is excluded, this 0 point. Now, if this alpha is positive, then we don't want them to intersect alpha times the unit ball here. So we have like these type of coverings all around this, which cover the unit sphere. And for negative alphas, the picture is something like this. But with whatever alpha we have, we can write it in terms of inequalities the following way, that there is a subset in the norm space X, which is at most countable, such that for every unit sphere, there is a point which satisfies this inequality. And this turns out to be, well, equivalent that if you can cover the sphere, then you can cover the whole space with this inequality. So quite a technical way to write it, but in the picture, this means this. Now this, what was our idea was somehow we observed that there have been many researchers working on octahedral norms and related notions, and there have been a lot of papers about ball covering properties, but we observed that we can make a unified notation for both of these theories. And with that, we were able to find some new results in both of these theories. So we will introduce the following notation. This C stands for covering, that you can cover the space with some set A, and alpha beta are some reals, if you have all of these points which satisfy this inequality. And for some cardinal kappa, we say that we have a covering of cardinal kappa if there is a set that belongs here. So with this notation, we see that X has this alpha PCP if and only if the unit sphere belongs to the covering of where alpha is minus alpha and beta is equal to 1. And this cardinal is just omega because it is asked about a countable covering. And so in other words, a unit sphere is a subset here if and only if we can cover it with balls centers at A and with such a radius. Now some properties about this notation. So the covering is the same if we take, instead of the set, its closure. If we multiply by a positive number, then this is still covered by this covering with the same cardinality. And well, what I also explained there. So combining these things, you see that covering the sphere is equivalent to covering the whole space. And this sometimes, well, this just makes sometimes convenient to write some proofs. And however, we will be later interested also in the negation. Well, from now on, mainly the negation of these things. So if a unit sphere cannot be covered by these kappa many balls, then this is equivalent to the fact that for every subspace of density kappa, there exists some X such that this inequality holds. So just to recall, the definition of octahedrality was that for every finite dimensional and for every epsilon, so you take alpha beta equal to some 1 minus epsilon, you have this. So this resembles more this octahedrality conditions. And now we define alpha PCP kappa in a very natural way. So instead of this original alpha PCP, we just, instead of omega, take an infinite cardinal here. Just consider more coverings. And in this notation, the Chang's original PCP is just 0 PCP omega. And this alpha PCP by Chang and others, and Kira Montesinos and Lisitsyn is just alpha PCP omega. And well, to summarize, we have the following. This property is equivalent that you can cover the sphere with kappa many open balls or closed balls. It actually won't matter. And well, the same if you cover the whole space. Now, what we will be also interested is a finite version of this property. So instead of having countably many or some large cardinal, we will consider this alpha PCP, well, less than omega, if the unit sphere can be covered with some finite number of balls. If you recall, this octahedrality was somehow similarly characterized, and we will soon see how we can write this in the same way. But just for background, just to remind that Chang proved that for a finite dimensional space with dimension n, then the unit sphere can be covered by at least n+1 balls. So you can't take less. And if it's smooth, then it's exactly n+1. So basically, he proved that finite dimensional spaces have this 0 PCP less omega, and if it's smooth, then it is exactly this. And he had some counterexamples that in general you can't get n+1. I think you should consider some two-dimensional L infinity probably. If I recall correctly, then this should give a counterexample. But why are we interested is that octahedrality can be characterized in this language the following way, that Banach space is octahedral if it fails this finite version of alpha PCP for every alpha. So and this will be the connecting point, how we connect these two theories about octahedral things and about PCB. And so what we were able to show was the following. So just to recall quickly, a Banach space is octahedral if it fails this alpha PCB. So we can rephrase Cottrau's theorem in the following way. If it contains, well, it contains subspace isomorphic to L1 if and only if it can be equivalent to real norm to fail this alpha PCB. And now we were able to extend this to larger cardinals in the following way. So X contains the subspace isomorphic to L1 kappa plus, where kappa plus is the successor cardinal. And X can be equivalent to real norm to fail this alpha PCB kappa for all negative alphas. So as you see, this is not exactly the same way. And this will be a question later that we don't know if this is also true for positive alphas. So at least our techniques don't work in that case. But for most of it, this is somehow in the same language we can define and extend it to bigger cardinals. So since this is an if and only if statement, then we will have two implications to prove. And let us start with the easier one, and which says that if a space fails this alpha PCB for some negative alpha, then it will have an isomorphic copy of L1 kappa plus. And the idea is from this paper by Giral, Lisitz, and Montesinos. They only consider this failing -1, so the extreme case when alpha is -1. And then they proved that if it fails the -1 PCB omega, then it contains L1 gamma, but an isometric copy of L1 gamma for some countable gamma. But these ideas also work here. And more importantly, we will later see that actually, if this alpha is -1, the extreme case is actually much stronger than these negative alphas, which are less than 1. So there will be spaces having this for negative, well, failing this for negative ones, but having for -1. So it is, in some sense, this is weakening. We weaken the assumptions, but on the other hand, we also get something weaker. We only get an isomorphic copy rather than an isometric copy. So what is the idea? We want to produce a set in the unit sphere of cardinality kappa plus, such that, well, the important thing is the right-hand inequality, such that it behaves like the canonical basis of L1 up to some constant here. This upper one is trivial. So we call this, well, the partially ordered set of all these sets satisfying this property G by P. And note that P is non-empty because you can take, well, just a single. And by Zorn's lemma, this partially ordered set contains a maximal element A. And now we have this maximal element A, and we assume by contradiction that the cardinality of A is less or equal than to kappa. We want to see that it has cardinality kappa plus. So since it fails this alpha PCB, then this was this proposition from in our preliminary part, and this says that you can find an element X, which is somehow orthogonal to everything here, where we take in every A and span of A. And therefore, we have that lambda X plus these linear combinations is greater or equal to, well, if it's bigger than minus alpha plus 1 times the norm of A, and alpha was negative up to -1, then this is also holds from the inequality. And now we see that Also, the union of A and this element X is in this our partially ordered set, but this contradicts the maximality of A because by Zorn's lemma we had that A is the maximal element. So therefore our assumption was wrong, and we must have that this set is at least of cardinality kappa plus. Okay, so we have this one way, and now for the other way, which is the more difficult one, that if you have a Banach space and infinite cardinal and X contains L1 kappa, then we can renorm equality such that it fails this alpha BCP eta for all alphas, and where eta, well, we all have this additional constraint that eta must be less than the cofinality of kappa. And this proof relies on this renorming idea, which I think first appeared in a paper by Kadet, Schepelska, and Werner, where they studied the thickness of the unit sphere and L1 types to, well, they actually proved many things there, but this technique has been really fruitful because it differs from the original proof that Godefroy had. And later on, this renorming technique has been used in, I think, in Doggerwet centers, studying Doggerwet centers. And very recently, I've seen this also with polynomial Doggerwet centers. And since Doggerwet spaces are spaces which have an octahedral norm, so it is very natural to suspect that something like this could work. And it turns out in our case, we can also reuse this renorming technique and to get our claim. So how it works? So we can first assume that we can renorm X such that it contains L1 kappa isometrically, and denote by E eta the characteristic functions or the basis functions of L1 kappa. Now consider the family of all semi-norms on X dominated by its norm, and such that they coincide with on this subspace L1 kappa. And let us take P to be infimum of all these semi-norms, then this is also satisfies these properties. And the key point is that with this P, we have that this limit is exactly the, well, not the norm, but the semi-norm of X plus 1 for all X. So this is the technical and hard part, mainly that this limit is what it is. And if you have this, then we can continue. So now we fix the set A and alpha. And then, well, by this definition of the limit, we had that limit of this is the semi-norm of X plus 1. Then we get that for all A, there exists an eta A such that this inequality holds for every bigger eta than eta A. And alpha is, well, you can, yeah, alpha is -1 and 1 between. So now when the cardinality of A is less than the cofinality of kappa, then by this definition of cofinality, there exists a theta, which is still smaller than kappa, but bigger than all of these eta A's. So therefore, for this E eta, we have the same inequality like we had here. And now what this inequality tells us that X with this semi-norm P fails this alpha BCP, basically. And now we want an equivalent norm, then we set this equivalent norm to be the sum of this semi-norm plus the quotient norm of X minus L1 kappa. And just to comment that this technique is actually quite expected, because these octahedral norms behave, and this failing of alpha BCPs behave the way that basically if you have a one sum, because if one of the components is octahedral or fails this, then the one sum will have it. So in a sense, this is very similar of putting one norm on this or something similar. And then it turns out that this renorming works. So now we will just have a look on some stability results. And just to remind, so recently Lua and Zheng proved that LP sum of a sequence of Banach spaces has this PCP if and only if each component has this PCP. And then when we consider, well, we will only consider this for L infinity and L1 sums because they were more interesting to us to get to produce these examples later on. So, but if it has this negative alphas, then it behaves similarly to the zero PCP. But for positive alphas, we have some errors here. So we have almost this alpha PCP. You get some epsilons. So they behave a little bit different to the negative alphas and positive alphas. And for L1 sums, well, this is written in the converse that if you can't cover one of the components, then the L1 sum also cannot be covered. So this explains what we saw in that proof, that if it fails for one component to have this alpha PCP, then it will fail for the L1 sum. And again, for the positive alphas, we have something that is almost like this. So it behaves a little bit weaker, that we get some error here, some alpha minus epsilon. And now to introduce some kappa octahedral norms and to show some examples where these spaces are, where these properties are all the equivalent, and also we will show that they, in general, they are different. So as I told earlier, then if you recall this proposition that failing alpha PCP kappa, if you take alpha and beta to be equal and take them to be equal to 1 and minus epsilon, then you naturally arrive at a very octahedral-like condition, which we call kappa octahedrality. So instead of finite dimensional spaces, you now have spaces whose density character is less than or equal to kappa. So you have some element which is orthogonal to every such subspace. So in our notation, space is kappa octahedral if and only if this unit sphere cannot be covered for all positive alphas and with kappa many balls. And if we look at the definition, then one implication is clear, that if a space fails this alpha PCP for every negative alpha, then this means that the unit sphere cannot be covered in such a way with minus alpha 1 kappa. And this implies that the unit sphere cannot be covered by minus alpha kappa, which by definition is kappa octahedrality. So just to notice, here we have positive alpha. So if alpha is negative, then minus alpha is positive. So maybe this could be a little bit with some better notation, but the idea is that you automatically get it by definition. And we will later produce an example where the converse does not hold. But first of all, I will have a look at some easier examples. Now, in the same paper, this Lua and Zheng studied stability of these PCP properties. And there they proved that this kappa is this PCP. And as I said before, so Dagobert spaces are special in this setting because if a space is Dagobert, has the Dagobert property, then the space and its dual both are octahedral. So, and this space, capital L infinity, is a space with the Dagobert property. And this property was introduced by Dogawet in '63, where he first observed that such an equality holds for in the space of continuous functions. So he first observed it here, but now we know that this extends to CK spaces where K has no isolated points, and L1 mu and L infinity mu spaces where mu has no atoms. So all of these classes spaces have the Dogawet property. But what is interesting is that already in, Kadich with Koisiratkin Werner, who have studied these Dogawet properties for many years and are probably one of the best experts on these. So they have this lemma that if X has the Dogawet property, then the dual fails the -1 BCP. So, well, of course, they don't use this language because it was 6 years before Cheng defined these PCP properties. But if you look at the statement of their claim, then it says this and actually a little bit more. But what we immediately get from this lemma is that capital L infinity, which is the dual of a Dogawet space, actually even fails the -1 BCP. So you automatically get something more. And now we will see that this space is actually a particular case of something more general. And for that, I will briefly recall that Lipschitz spaces. So if M is a metric space and we fix a point 0, then the Lipschitz space which send this fixed point to 0 is a Banach space with the usual Lipschitz norm. And now, if you recall that capital L infinity is isometric to Lipschitz to the space of Lipschitz functions on the unit interval of 0, 1, then actually we have something more general. So the following are equivalent. So the Lipschitz space has the Dogawet property. It is octahedral. It is omega octahedral, and it fails the -1 BCP. And the proof for us is simple because it relies on a work done by many authors. And the proof is the following. So the equivalence of 1 and 2 follows from a paper of Aviles and Martinez Cervantes. It is not explicitly stated this way, but it follows from there. And they all also behind this, the equivalence of 1 and 2 are the work of many authors. If I recall correctly, then Garcia Lirora, Tony Prohaska, Rueda Zocca, Kadets, Ivano, and Werner. So there are many authors behind the equivalence of 1 and 2. So for us, it is easier to add other equivalences. So first of all, 4 implies 3 and 2 is clear by definitions, as we saw earlier. So what is left to prove is that 1 and 4 are equivalent. So to prove that 1 implies 4, notice that the Lipschitz space is actually a dual space. We have had here many talks on Lipschitz free space. So I will not define it here, but it's a dual space. Now, since the Lipschitz space has the Dogawet property, and it is known that the Dogawet property passes from the dual to its predual, then we have that the predual has, the free space has this Dogawet property. And by this lemma, by Kadets and others, we get that it's dual. So Lipschitz space must fail the -1 BCP. So combining these observations, we get that in the class of Lipschitz spaces, all of these notions are the same. Now, however, in general, we have the following diagram that this is the strongest one. Well, we just saw that for Lipschitz spaces, all of these 4 properties coincide. Well, kappa is omega. But in general, we will see that this we have different properties. And some easy examples first. So little L1 is octahedral. but of course it is not even omega octahedral, because no space can be the same, can be density X octahedral basically. So if it's not omega octahedral, then it's not kappa octahedral. And of course it doesn't contain L1 kappa plus. So you get that X is octahedral does not imply this and does not imply this. Now L infinity kappa contains L1 kappa plus. So we have something here, but it fails to be octahedral, and it has this finite version of AlphaPCB for all alphas. Okay, so I have here written the proof why this L infinity works, but this is quite technical, so I think looking at time, I will skip it right now and continue with the more interesting examples. So we were able to show that for every kappa, there exists a Banach space which fails this AlphaPCB for all alphas and all negative alphas, but it has the -1. So this is a strictly stronger property having this -1. So you can get how close you want to -1, but not -1. And how to produce this space is the following way. You consider L1 kappa plus with a new norm, which is one norm combined with the infinity norm in such a way. And then by calculating, you can show that it fails this AlphaPCB kappa. Again, mainly by this part. This makes it fail. And this infinity part will make sure that you can't get -1 here. So it is covered by this finite number of elements. And now to finally to have this space, you fix a sequence whose infimum is -1, and take X to be the L1 sum of these X alpha kappas. And then you get this example of a space that satisfies these conditions. And now to show that kappa octahedrality is weaker, we do some similar tricks. We also consider L1 sum, but we build it up on a different building block. So we take R from the interval 1/2 and 1, and kappa an infinite cardinal. And then we set P to be something that works, let's say like this. So P works, and you take XR kappa to be the LP of kappa plus. Now, this XRK cannot be covered by this with RR kappa. On the other hand, since it's an LP space, then it is reflexive. Therefore, it does not contain L1. And if you recall, we proved that if a space fails this AlphaPCB for some negative alpha, then it must contain L1 or even L1 kappa plus. So if it doesn't contain L1, then by contrapositive, you get that XR kappa has this AlphaPCB for all of these alphas, for all negative alphas. And finally, you fix a sequence Rn in the same interval such that the supremum is 1, and again take the L1 sum of these building blocks, and then you get a space which is kappa octahedral but has this AlphaPCB for all negative alphas. So this way you produce this for every infinite cardinal, you can produce them. And now finally, to finish with some open problems. So just to summarize what we showed that if a space contains L1 kappa plus, then we can equivalent renorm it to get as close to -1 as we like. And we just saw that without renorming, there are spaces which fail this -1 PCB, well, almost this -1 PCB for every epsilon, but have this -1 PCB. So a very natural question is that, can you improve it, and can you renorm every space such that it fails this the strongest one, the -1 PCB. And right now we don't know if this can be done. And the other question is revolves around the converse. What I mentioned earlier, what happens? We were able to renorm for all negative alphas, but what happens for positive alphas? And positive alphas correspond to kappa octahedrality. In a sense, you would expect, well, if in an ideal world that you can, this Godfrey's original theorem was stated in the language of octahedrality. So whether you can do the same here, so you can characterize it with kappa octahedrality. So we saw that if it fails for some negative alpha, then it contains L1 kappa plus. Now, if it fails for every negative alpha, then this implies kappa octahedrality, as we saw. And however, we saw that kappa octahedrality is weaker than this failure for every -1 PCB. So there were these counterexamples. So therefore, my final question is, if a space is kappa octahedral, then does it always contain an isomorphic copy of L1 kappa plus? So if you get this, then you get almost well, you can write out the theorem in the same way that Godfrey had it for octahedral norms. But we don't know also that at the moment. So that would be all from me, and thank you for listening.
Thank you very much, Johann. Are there any questions? Then I may ask a question. So you have this one theorem where there are 4 equivalent properties for spaces of Lipschitz functions.
Yeah.
Octahedral, omega octahedral, and some of these BCP properties. Do you know if this has any gives any information about the complete metric space, or is this?
Yes. Actually, there is a metric. Well, there is a metric characterization of spaces having the Doggerback property. So these are these length spaces. So you can so you have this also for the metric space. Yeah.
So, but this is a metrical characterization of Banach spaces. But what about the metric space inside Lip0M? Like,
yeah, this is what I mean. You get
I see.
This the Doggerback property of Lipschitz space is equivalent to the fact that the metric space is a length space.
Okay.
So, but this has been done by this Aviles and the other authors that I mentioned before. So, and Kallens and Werner and a lot of guys.
Thanks.
But just here in these spaces, this is not the first time that all these properties coincide. So if you recall Ramon Aliaga's talk, then in the predual in the free space, the Radon-Nicotin and Schur properties and a lot of properties coincided. So.
Well, thank you very much. If there are no questions, I'm going to stop the recording.
Thank you.
And